All right, good morning, everyone. We're going to start off with some more review questions today, and then we will be talking about let's see, Cartesian coordinates and distance, solving linear equations in one variable, and solving rational equations. If you also saw, I made a submission available for quiz one and a submission available um, for worksheet one, and you should be able to submit your files there. I've set it up only to accept PDF files because sometimes other file formats will mess something up as it converts, and I won't be able to see it, and then I have to send a bunch of emails to different students to have them re-upload it. So just make sure it's available in PDF format. You can, if it's a different form, you can usually pretty easily convert it. And so they're both available now. And I think I have the quiz due Monday at midnight and the worksheet due Sunday at midnight. So you have some time to do it. Once you open the quiz, there's no time limit. You can do a little bit here and there and submit it at the very end. But the exams will be a little bit different. Once you open it, they'll only be available for a certain length of time from the time you open it. So you won't have, for example, like a couple of days to do it. You'll have probably like 2 hours to complete it, and I've given you 2 hours so you can have time to work on it, and then have time to upload everything, because sometimes that can take a while. So let's plop down these review questions now. Okay, so these questions are all similar in various ways. I've just added slight variation in really the same question. This is the base question, and I just want to show you that even when I change up the signs, for example, when these are both negative, or when I rearrange the order of the radical, or maybe both terms in the denominator are radicals, the question doesn't really change. We're going to be using the same principle as before. So remember, you cannot have radicals in the denominator. That's the standard that we set for fully simplified. So all of these have radicals in the denominator, so we need to get rid of them in some way. And these, maybe I'll add just one additional example. So we'll start off with this example, actually. Anyone want to throw out a suggestion on how to simplify this so I don't have this root 17 in the denominator?
You multiply by 17, like
Uh,
at the top, like you multiply root 17 to both sides.
oh yeah, to both sides of the fraction. So what I'm going to do is multiply by root 17 over root 17. So remember, with a fraction, the only thing I can do to it is multiply it by something that's equal to 1. And this fraction right here is equal to 1. So I haven't changed the equality of anything yet. But now what happens is, in the numerator, I get negative 8 times root 17. But root 17 times root 17 is negative 8 times root 17 over 17. The root 17 times root 17 just becomes 17. It just becomes what's inside. And this is simplified enough. We no longer have the radical in the denominator, and we're good. But these questions are a little bit different because I can't just multiply by root 17 over root 17, because when I distribute that root 17 inside this quantity 1 minus root 17, I'll actually still have the radical in the denominator. So we're going to use the fact that a squared minus b squared is a minus b multiplied by a plus b. So here I have a minus b. It's a quantity minus another quantity. So what I want to do is multiply the denominator and the numerator by a plus b. So I get a squared minus b squared. And notice, since this is a root, once it becomes b squared, the root will go away. So that's the big advantage. So I'm going to multiply this by 1 plus root 17 and 1 plus root 17. So now based on this formula, I'm going to get 8 times the quantity. Be careful with your parentheses. Whenever you multiply by sum or difference of things, you always want to make sure you have parentheses around. But what happens is, when I multiply the denominator, I get 1 squared minus root 17 squared. That's 8 times 1 plus root 17 over 1 minus 17. That's 8 times 1 plus root 17 over negative 16. So that's 1 plus root 17 over negative 2 when I cancel the 8 and the 16 with a factor of that. And this pattern is what will happen with a lot of these questions. So how do you think I should change this question in order to correctly multiply by some like a plus b over a plus b, or maybe a minus b? This looks like something similar in one of your worksheets, so this is probably useful for you guys to consider. Let's factor a negative out. So all I did was I took out a negative 1 from the numerator and a negative 1 from the denominator. And then what happens is both of the signs flip in the denominator. This works because this is a negative and this is a negative. And then they get canceled as 1. So now what should I multiply this fraction by? So here I have a plus b. What do I want right here?
A minus b?
Yep, a minus b. So I'm going to multiply by 4 minus root 17. 4 minus root 17. Remember, it has to be a fraction equal to 1. So now I get 8 times 4 minus root 17. And then in the denominator, I get 4 squared minus 17, the root 17 squared. Right? A plus b times a minus b is equal to a squared minus b squared. That was the point of this formula. We'll simplify that out a little bit, but we've got into the crux of the problem now. Since 16 minus 17 is negative 1, this is going to be negative 8 times the quantity, 4 minus root 17. What about this one? What should I multiply this guy by? Any suggestions? So nothing has really changed. It's just that the root is now in front instead of the back. So let's do it. We're gonna, since this is a plus b, we're gonna multiply by a minus b. A minus b. Nothing really changes. So now I get 8 times the quantity root 17 minus 4. Then I get root 17 squared minus 4 squared. And I arbitrarily decided to simplify this more. You don't have to do, you can leave it just as we had above. What about a number like this, where we have 2 roots rather than a singular root? What should I multiply this by? Any suggestions? The hint is that the pattern continues. So I'm going to multiply this by root 17 plus root 5, and this by root 17 plus root 5. Them both being radicals actually doesn't mess us up at all, because when I apply the a minus b times a plus b being a squared minus b squared, both a and b being radicals is not an issue for us, because when I use the formula, they both end up getting squared at the end. So both radicals will disappear anyway. And that's equal to whatever it is. We don't need to worry about the last bit of arithmetic. So any questions about these? I noticed that a lot of students struggle with this concept, so I wanted to kind of reinforce this approach, and um, I added just very slight variations. If you look at the worksheet, I do have some questions like that where I'll just change one sign of one question or something like that, and I'll see if you can contrast, how the really small, minute characteristics of the question change when I switch a sign or switch a position of something. And that's what these examples are about. I've basically stuck with the same structure. It's just changed a little portion of it, and that changed our approach. And that's what math is about, right? It's about learning how to solve not just a single question, but then how to use those techniques to solve other questions as well. All right. Any questions on that? I am scrolling down to get access to a couple more questions. We need to talk about simplifying rational expressions some more. Okay. Some more review. Ooh, I think we did that one. 2 over a plus 7 over b over the quantity b. And then I'll make one up. Okay, so does anyone remember the general approach on how to simplify rational expressions like this? These are specifically simplifying complex rational expressions where we have a fraction over a fraction. So the general idea is to combine as much as we can and then write this as division and then reverse the division and make it as a statement about multiplication. So we need to simplify these guys' numerators first because they are separate fractions. I want this to be a singular fraction over a singular fraction. So how should I combine the numerator up here? How do I add 2 over a plus 7 over b?
Would that turn into 2b plus 7a?
Yep. So what we're going to do is multiply 2 over a by b over b. And we're going to multiply 7 over b by a over a. So yesterday, I think another student was able to go directly to the answer, and that's fine as well. But this is the general approach on how you always do these type of questions. You guys know how to cross multiply and get that common factor and add right away, and that's fine as well. It's just some questions will be slightly uglier and it will be a little harder to recognize. So I want to give you the baseline approach, but what you guys are quoting is the result, and that's also okay. But if you look right here now, in this denominator and this denominator, I have the same quantity, a times b. So what I can do is just add through their numerators now. So now I have a singular fraction over a singular fraction. So I'm going to rewrite this as 2b plus 7a over a times b divided by b, or if you want to write it as a fraction, b over 1. I changed this division into multiplication by flipping that value. So the reciprocal of b over 1 is 1 over b. So our final answer is 2b plus 7a over ab squared. We're going to do the same thing over here, and we'll use your guys' technique of just going straight to the answer. If I always multiply this factor up here and this factor up here, you can just add these fractions together. So this is 8x minus 4p over 32, which is 4 times 8. If you use this approach by multiplying by the missing factor you see, you'll get to this exact same result. Over p. This is 8x minus 4p over 32. And we're going to extrapolate from this formula up here. Notice when I divided by b, what happened really was I ended up multiplying by 1 over b. It's reciprocal. Dividing by b, multiplying by 1 over b. Dividing by p, multiplying by 1 over p. So I get 8x minus 4p over 32p, and you're done. Not bad. This one's a little uglier. So again, I want to write this as a singular fraction divided by a singular fraction. That is our guiding light through these difficult questions. So how do I get this complex fraction as just a singular fraction over a singular fraction? We're going to combine the numerators and denominators. So I'm going to take this one a little slower because the x's and the y's are kind of confusing. So the common denominator between y and x is y and x. So I'm going to multiply by equivalent terms to get me there. So I multiplied the numerator and denominator by a quantity equal to 1, but notice now I have y times x and y times x as a common denominator. We're going to do the same approach up here. So I can do these things for free because I'm only multiplying things by 1. No quantity is actually changed. So in the numerator, I have x squared minus y squared over the quantity x times y. That's combining them under the same denominator. And up here, I have x squared plus y squared over x plus y. So what is the quick dirty trick in how to make this division multiplication? So dividing by this quantity is the same thing as multiplying by its reciprocal. And its reciprocal is when I just flip the fraction. Is everyone okay with that step? If you can drop me a thumbs up for that, let me know. Okay, I have 1 thumbs up. Would anyone care to explain where you're lost in this question? I have more thumbs up. Okay. So just remember, dividing by a quantity, dividing by a fraction is the same thing as multiplying by its reciprocal. So dividing by this ugly fraction is the same thing as just multiplication of its flipped fraction, its reciprocal. And now we can do a little bit of cancellation. That cancels with that, and that cancels with that, because they can factor away as 1. But our final one, can I cancel that and cancel that and cancel that and cancel that?
No.
No, right? Because the only way I can cancel things in fractions is if I can factor them out as through multiplication and then cancellation. But here I just have a sum and difference of 2 different numbers, and there's no more simplification that can be done. So this is your final answer. Let's try this. So up here, if you noticed, we only had to do simplification in the numerator and then rewrite it as the division is multiplication. And then here we had to simplify the numerator and denominator. And then here we only have to simplify the denominator. So let's do that. And this is where that quick and dirty rule is a little bit harder to recognize, because now you have these quantities, x minus 3 and x plus 3, but it is at the heart the same idea. What I'm going to do is multiply this quantity. Maybe I'll use a different color to emphasize that. X plus 3 over x plus 3. I'm going to multiply this quantity by x minus 3 over x minus 3, because in this question I want to combine this numerator and denominator, and I need a common denominator to do that. And in order to do that, I'm going to multiply by the missing term to make them have like denominators. So since they have like denominators now, I'm going to just add through their numerators. But this is where parentheses really matter. When you multiply by a sum or difference of terms, you need to have parentheses. Otherwise, you're going to lose some values. So this looks really ugly, but don't worry, life will get better. Let's do some arithmetic inside this guy's numerator. I'm going to distribute that 5 to get 5x plus 15 plus 6x minus 18 over the quantity x minus 3, x plus 3. And I'm going to continue to simplify it in the very bottom denominator as much as I can. This will become 11x minus 3 over the quantity x minus 3, x plus 3. So now, how do I rewrite this division as multiplication?
Multiply by the reciprocal.
Yep, exactly. So now I'm going to take that bottom fraction and reverse the numerator and denominator. And now we're to a question that's just about simplifying rational expressions. Now what we can do is cancel this x plus 3 and this x plus 3. And you're done. That's as simplified as it gets. So just remember the overall approach on how we do these questions. Don't try and memorize this question. Try and think about, how did I solve a question like this in class? So on the worksheet and your quiz, you're going to have some questions like this, and think about, okay, how do I use the underlying technique to solve this question based on what we've seen? That's what math is all about. Any questions on these examples? Okay. As always, feel free to interject at any moment. So we're going to be talking about Cartesian coordinates and distance. Solving linear equations. And then solving rational equations. So now we're getting into some harder stuff. So, maybe I can change the template and that will actually give us a little bit easier time. Okay, cool. So, in math, it's actually very powerful to be able to talk about distance. Distance is a very important concept for obvious reasons. And we can talk about distance if we were to plop some type of grid like this through two-dimensional space. So on these lines represent different values of x and y. You guys will probably be quite familiar with this already. So we'll just talk about this area for now. So this coordinate system is super powerful because if I say, maybe I should make this like thicker because it's the axis. If I say every value along this dimension of movement represents an x value, and every dimension of movement along this dimension represents a y value, this is enough to help me describe any point on this plane of existence. So if this represented like your table, I could tell you if I go to, I could give you coordinates for this point right here, and you could define that point exactly. You know exactly where that is, and that's really powerful in math. So what we do is call this like 1, 2, 3, 4, 5, 6, 7, and this would go on forever depending on how big your desk is. This would be 1, 2, 3, 4, 5, 6 at these points right here. And again, it would go on forever. And in this direction, we would have -1, -2, -3, -4, dot, 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 going on forever. Here we have -1, -2, -3, -4, -5, dot, 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 dot. So at this very center where these two lines intersect is 0 in both x and y. So it's 0 in y and 0 in x. So now that we've developed this coordinate system, I can tell you, oh, your coffee cup is at the point 2, 2. And this is how we denote a spot on this coordinate plane, 2, 2. Or in this case, right here, this would be 3, 4. So we denote the x value first. The x value is at 3. And the y value is at 4. So any point on this axis or on this coordinate plane is always going to be of the form x, y. So how would I write a coordinate for this point right here? What would the coordinate be?
One comma -3.
Yep, 1, -3. And then like over here, for example, would be -4, 3, -3. How do I define a point that's on an axis? That's kind of weird, right? What would this xy coordinate be? So notice, oh, Hannah, did you want to provide an answer?
Yeah, 0, 4.
Yeah, 0, 4. So notice along the y-axis, all of the x values are 0. They're forced to be 0 along the y-axis. So right here is 0. The x value must be 0 to be exactly on the y-axis. And then the y value is 4. Similarly, being on the x-axis, the y value is forced to be 0. So this point is 6, 0. So that's cool and all. Now, we've learned how to define points on a coordinate system, and now we can talk about distance between 2 points on a coordinate system. So the difference between your keyboard and your coffee cup. So let's do it. Let's figure out, how do I describe this distance between these 2 points? That's a wonderfully straight line. Let me try something else. There we go. So distance is really important, obviously, if you're going to define points in the plane of existence, talking about how 2 different points change matters. For example, so in higher level mathematics, you're going to not talk about planes, but surfaces. So for example, if I were to take like a piece of paper and bend it like this, no longer can I describe distance as the difference of these 2 points, for example. It doesn't work anymore because the surface has curvature to it. So the distance doesn't make sense anymore. And that's what a lot of higher level mathematics is about. It's talking about distance over what we call manifolds, which are weirdly shaped spaces. So I'll give you the formula. The distance between 2 points, we'll call it D, is the square root of x2 minus x1 squared plus y2 minus y1 squared. And what these little subscripts denote is that they are different x and y values. So the difference between the distance between x2 and y2 and x1 and y1. So it just helps me organize which x and which y I'm talking about. It's just a label. It's not an exponent. It's not the opposite of an exponent would be. I don't know, but it just helps us keep the correct orientation. So let's think about the distance between these two values, 2 comma 2 and 1 comma negative 3. So 2 comma 2 and 1 comma negative 3. So here I have x1, y1, and x2, y2. I could switch this and call this x2, y2, and this x1, y1. It doesn't matter how I labeled them originally, so long as I keep them in the correct little packet of numbers. So if I accidentally put x1 here and y1 here, you're going to get a different value. It needs to be x2 and x1 and y2 and y1. So let's plop it in. Which is why also it might be helpful for you guys to label them yourselves right here. If you're asked to find the distance between 2 points, just plop those little parentheses right there, label them, and then it's just fill in the blanks. So here's x2, which is 1, minus x1, which is going to be minus 2, plus y2 is going to be negative 3, and y1 is going to be 2, so minus 2. So 1 minus 2 is going to be minus 1 squared, and minus 3 minus 2 is going to be minus 5 squared. Notice though, I need to do all the simplification inside the radical first. I can't do this. This is not a correct application of the formula. If you remember, this is what I specifically warned you about. This is not true. What we need to do is simplify inside the radical first. Minus 1 squared, is going to be positive 1. Minus 5 squared is going to be positive 5. So this is root 6, and you're done. So the distance between this point and this point is root 6. Here's another formula. Let's talk about the midpoint between these two values. So this is the distance formula. Here's the midpoint formula. So again, between x2, y2, and x1, y1, just two random points that you pick. The midpoint between these two is really just the average of the 2 points. So let's find the midpoint between the original 2 points that we had. So here's 2 comma 2 and 1 comma negative 3. These were the 2 points that we had. Let's just plug it in. So the midpoint is going to be the x values added together divided by 2. Wait, is the last one supposed to be 25 instead of 5? Oh, you're right. I'm so sorry. Thank you. Yeah, sorry, that is my mistake. Does everyone see the mistake that I made? I just want to clarify so everyone make sure that they see what I did wrong.
Yes.
Okay, yeah. So I accidentally wrote 5 instead of negative 5 times negative 5, which is 25. So this is root 26. If anyone has any clarifications, let me know. So back to this question, what I'm doing is I'm adding the 2 x values together and averaging them. I'm dividing by 2. Same with the y values. I'm going to add the y values together and then divide by 2. This is 3 halves. And this is minus 1 half. So this is the midpoint. Between 2 comma 2 and 1 comma negative 3. And I guess I should explain what a midpoint is if it wasn't clear by the name. The midpoint is just going to be like this guy right here. It's the point exactly in the middle of the 2 points. And actually, that kind of looks like it matches up, which is, always cool. This x value right here is like 3 halves, and this y value right here is like negative 1 half. So I don't plan on spending too long on these questions. I think they're pretty self-contained. You're always going to be using these 2 formulas. Maybe it's worth just doing one more. Let's see here. Okay, so the advantage of these formulas are we don't need to draw a huge grid system in order to understand. We can just apply the formulas and we will understand the space that's involved perfectly fine without having to draw it. So let's find the distance between negative 4 and 1 and 3 and negative 4. So I don't need to draw this anymore. I can just plug them into the formulas. I'm also going to go back to the line. So let's call this x1, y1, and this x2, y2. Remember, it doesn't matter which one I call which, so long as I have all of the x1s and y1s in one bubble and all of the x2s and y2s in one bubble. I could reverse it and call this x2, y2, and this x1, y1, whichever you prefer. So the distance formula, is the square root of x2 minus x1 squared plus y2 minus y1 squared. And we're just going to plug in now. x2 is 3. And this is where you have to be careful with your arithmetic. x1 is minus 4. So I'm subtracting minus 4. y2, which is minus 4, minus y1, which is 1. So inside this parentheses, this becomes 3 plus 4 squared because I'm minusing minus 4. This becomes minus 5 squared. This is the square root of 7 squared plus 25. This is the square root of 49 plus 25. That's 54, so that's 74. So this is the square root of 74. Let's see, are there any factors of 74 we can take out? This is more for your Newton Alta. Sometimes Newton Alta will want you to simplify this expression more. 30, so this goes into 37. Yeah, so it's 1, 2, 37, and 74. Those are the factors. I don't think it has any other factors. So there are no perfect squares that I can remove. So this is as simple as it gets. And then we can find the midpoint. So it's going to be x1 plus x2 over 2. Add y1. I guess y1 is technically 1. y1 plus, so I'm going to write that minus because it's adding a negative 4 over 2. So this is going to be negative 1/2, negative 3/2. And that's the midpoint. Any questions on this? I think this is a fairly straightforward concept, nothing too tricky. Okay, so now we're getting into something that's much different. Now what we're going to be doing is solving equations. All that we have been doing so far is getting some groundwork done on how to simplify things, but we have not actually solved any equations. We've only made things easier to read and write. But now what we're going to do is shift over to solving equations where we need to solve for a certain value. So as an example, this is a linear equation that we can solve. Notice this is an equation because I have this equal to something. Everything that we have done so far while we've written equalities have not been necessarily solving for something. We used equality to say these were the same thing as I wrote in the previous line, but now this is going to be solving for an x value. This equality is true sometimes, and it's true for certain values of x. What we're going to do is use some careful algebra and arithmetic in order to solve for what x should be to make this statement true. This right here. This is a true statement. Sometimes. We need to solve for when. So let's do some arithmetic and some algebra. So I want to solve for x. So my general goal will be, I can write this in green. isolate x. This is the guiding light to solving any type of equation. Isolate x. The isolation sometimes is a little difficult, but that is the end goal. So what I'm going to do is get rid of this minus 5 by adding plus 5. But since I add plus 5 on this side of the equation, since I add plus 5 over here, I need to also add plus 5 over here. That's how I maintain equality. When you have an equation, whatever you do to one side, you must do to the other. So now that minus 5 and plus 5 cancel, but on the right-hand side, I get 15, because 10 plus 5 is 15. So now I've isolated x. All I need to do is divide by 2. But remember, if I divide by 2 on the left side, I need to divide by 2 on the right side. So when x is equal to 15 over 2, this is a true statement. So this is what we call a conditional equation. Meaning it's true sometimes. We can solve for when that sometimes is. Let me give you another example. So what we're going to do is try and isolate x as much as we can. And the way we do that is just try and cancel some things. But notice right here, if I subtract 7x and 7x, right, I'm doing the same thing to both sides of the equation. So it's a valid operation. This is okay to do. But I get this weird cancellation of all the x's. All of the x's disappear. And I get 2 is equal to 5. And can this be true? Is this a true statement?
No.
No, right? It's false. This is something that's never true. This is never true. This is called an inconsistent equation. It's never true. We have one more example. Something like this. So I have x's everywhere, but let's just try and combine as much as we can. If I just simply add the right-hand side together, I get 5x is equal to 5x. And there's no more arithmetic to really do. I could, for example, divide by 5x if you wanted to, just to drive the point home. And you would get 1 is equal to 1. And this is something that's always true. This is an identity equation. They're true regardless of any value of x. So this doesn't matter what x I put in here. If I put any x in here, this is always a true statement. So it's an identity equation. So just to recap, conditional equation. This is the one that we're going to be dealing with a lot. A conditional equation is an equation that we can solve. It's something that is true some of the time, and we can solve for when that some of the time is. An inconsistent equation is something that has no solution, meaning it can never be true. And then an identity equation is something that is true regardless of what we solve for. It will always simplify to something like this. It will simplify to a statement that is just true regardless of any value of x we pick. So let's do some practice. Let's see here. Get We're going to do a couple introductory examples, and then I'm going to move over to solving rational equations, and then we'll do a couple more harder examples of both categories when we meet on Monday. So, what is the guiding light that I mentioned on how to approach these questions?
Isolate x.
Yep, we want to isolate x. So in order to isolate x, though, if you notice, x is kind of trapped inside these parentheses. So I'm going to expand these parentheses and try and just collect all the terms that have x on one side and all the terms that don't have x on one side. That's isolating x. So I'm going to distribute this 4 to get 4x minus 16 plus 12 is equal to 15. And be careful, this is a minus 5 out in front. So when I distribute this, I get minus 5x minus 30, minus 5 times 6. Here's an x, and here's an x. Here's some stuff that doesn't involve x, and here's some stuff that doesn't involve x. So if I combine some things, negative 16 plus 12 is 4. 15 minus 30 is minus 15. So that's just me combining things on the left side and the right side. Now we're going to do some arithmetic. I'm going to get rid of this 4 on this side by adding 4 to both sides. That once we shove something to the other side of an equality, this is how we do it. That we get rid of it by doing an opposite operation, but to both sides. So subtracting 4 over here, I can undo by adding 4 over here. But in order to do, I need to add 4 to both sides. So I get 4x on the left-hand side is equal to negative 11 minus 5x. Now, I want to collect all of the terms that have x on one side. So what I'm going to do now is add 5x. So I get cancellation here, but 4x plus 5x is 9x is equal to negative 11. The last step, divide by 9. So this is a conditional equation that is true when x is equal to negative 11 over 9. Let's try another one. Negative 2 times 3x minus 1 plus x equal to 14 minus x. Wow, this handwriting is especially bad today. So guiding light, I want to collect all the x's on one side and shove all the things that don't involve x on the other side. But in order to do that, I need to expand this parenthesis as much as I can. And now there are a couple like terms, or one like term on the left side I can combine. X minus 6x will give me minus 5x plus 2 is equal to 14 minus x. So now I can start doing some algebra. In order to get rid of this negative x on the right side, I'm going to add x to both sides. So I get negative 4x plus 2 is equal to 14. Now I want to get rid of this 2, so I'm going to subtract 2 from both sides to get negative 4x is equal to 12. Last step, divide by negative 4. to get x is equal to -3. And that's your final answer. So these are linear equations because they describe straight lines. What we're looking at is if I were to draw, again, that like grid of space that we had. These equations describe lines going through that space. And then we have another line going through that space. And what we're looking for is, when are they equal? When do these lines intersect? When do they have the same value? So this is what this is. This is some line, and this is some line. Maybe it looks like this, and then maybe this line looks like that. They will intersect at the point x equals -11/9. That's the idea. And that's why it's called solving linear equations, because they describe linear lines, straight lines. But now, of course, we get to talk about a harder topic. Solving rational equations. I need to check something on the worksheet quick. Okay. So depending on how far we get into solving rational equations today, I might push the due date to the worksheet until Monday rather than Sunday, just because at least on Monday, then we can talk about some of the harder examples, because there's a couple hard ones in there, and I don't want you guys to be struggling with that. So a rational equation, that means that there are x's to solve for in denominators. That's why it kind of sucks, because solving them is a little bit more difficult. So seven over 2x minus 5 over 3x is equal to 22 over 3. So this is hard, because now I'm left with, how do I solve this? Should I combine these fractions, and like how do I get this x into the numerator to solve for? Because I can't write this as a nice x equals something, because x is in the denominator. So the trick is to multiply through the entire equation by some common denominator. So let's do that. In this case right here, since this already has a 3, the least common denominator is going to be 2x and 3x. Or I'm sorry, 6 times x. You could think of this as 2 times 3 times x. Those are all of the unique factors of every denominator. But the trick is, I need to multiply 6x through the entire equality, right? Not just the left side, not just the right side, but the entire side. So that's why I put these big parentheses out in front and multiply by 6x. So now I'm going to distribute the 6x. 6x times 7 is going to be 42x over 2x minus 30x over 3x is equal to, and I'm going to leave it in this format. So what was the big key in this step? Notice in these values over here, where x is in the denominator, by multiplying through by this guy, these x's are about to disappear. and then suddenly reappear inside the numerator of this side of the equality. So now I can solve this like a linear equation. Let's expand on that. This is now going to be 21 minus 10 is equal to 22. And what I can do right here is cancel a 3 and a 3 here to get 2. So 2x. Now this is a regular. So I did 6x because if I look at the common factors between 2x, 3x, and 3, the unique factors are 2, 3, and x. 2 times 3 times x. So 6x. I don't need to do necessarily the least common denominator. You could multiply through by the greatest common denominator, which is just all of the denominators multiplied. This was just a convenient one. We'll do a couple more examples where maybe it doesn't work out like that. But now that I've multiplied through by this nice factor, this is just a linear equation to solve. This is a 11 equals 44x. Divide by 44 to get 1/4 is equal to x. So x is equal to 1/4. That's my final answer. Let's try another one. So I'm just going to show you that it need not be the least common denominator. I can just, I think when I described this last semester, I'm just going to just destroy the entire equation by multiplying through by the common factor, which is all of the denominators multiplied by each other. So I'm going to multiply this by 3x times 4 times 6x, just getting rid of every denominator as much as I can. This is still a fine operation. It's just maybe not having the least common denominator will make it a little bit more tedious for you. So I'm going to distribute this 3x times 4 times 6x to every part of the fraction. So this is 2 times 3x times 4 times 6x over 3x. That's the first part. Is equal to 3x times 4 times 6x over 4. Oh, did I accidentally make this a quadratic equation? I think I might have accidentally made this ugly. Yeah, I think this is going to involve a technique that we have not discussed yet. Yeah. Okay, never mind. Sorry, we had to scratch that question. I accidentally designed this question in a way that won't work out for us. So that is my mistake. So let's stick with the least common denominator. It will, or the least common multiple. It really does work out for us. So between the factors x, 10, and 4x, What is going to be the least common multiple of this? Any suggestions? Probably 20x, right? So since x exists in these multiples, I will have to include x no matter what. So the crux of it comes down is what is the least common multiple between 10 and 4? So if I list out some multiples of 10, I have 20, 30, but here I have 8, 12, 16, 20. So this is going to be the least common multiple between them. So I'm going to multiply through by 20x and get some wonderful cancellation. So I skipped a couple steps just for the sake of time, but all I did was distribute this 20x into every term in this equation. Get some cancellation with these x's. To get 20 is equal to 2x minus 15. I'm going to add 35, not 35. I'm going to add 15 to both sides to isolate x. So I get 35 is equal to 2x. And the final step, division by 2 to get x is equal to 35 divided by 2. And that's my final answer. Okay, so if you notice right here, these are always a rational term equal to a sum or difference of rational terms. But actually, sometimes it works out in a slightly nicer way. If I have a singular fraction equal to a singular fraction, so let's say I have 2 over x is equal to 7 over 9. So if you compare, this is a sum, or this is a difference of fractions equal to a fraction, but this is just one fraction equal to one fraction. And what I can do is cross multiply in this situation. Cross multiplication is when I multiply that over to that numerator and then multiply that over to that numerator. So when I cross multiply, I get 2 times 9 is equal to 7 times x. That's me multiplying their denominators over to their numerators. So I have 18 is equal to 7x. So x is 18 over 7. So this is an easy case when you can cross multiply. And we'll use that technique a couple more times as well. So here is where it gets trickier. Now I have this sum and difference, or in this case, I have a difference of a binomial expression inside the denominator here. I no longer have just x or 2x or 6x, I have x minus 6. But since I still have a singular fraction equal to a singular fraction, I can just cross multiply. But be careful. It is a quantity I'm multiplying through, so this is 3x is equal to the quantity 5 times x minus 6. But now we've arrived at a linear equation that we know how to solve quite easily. This is 3x is equal to 5x minus 30. So I'll subtract 5x over to isolate the terms that have x to get negative 2x is equal to negative 30. Divide both sides by negative 2 to get x is 15. Any questions so far? Okay. Let's try another example. But here is where it actually gets ugly. These are the hard ones. Let's see. X over x minus 2 is equal to 5 times x minus 2 divided, or minus 1/2. So let's go back up and consult our previous examples to see if we have some type of concept that we can extrapolate. So what did I do here? When I had a fraction, a rational expression minus a rational expression equal to a rational expression, what did I do? I multiplied through by the least common multiple. So let's go down here and try that. The least common multiple between x minus 2 and 2 is always just going to be their product. So when I have binomial expressions in the denominator, the least common multiple will be always easy because it will always just be the product of all of the denominators. So here's x minus 2 and 2. So all of the unique terms, I'm just going to take all of them multiplied by each other. And I'm going to do that same thing we did before. I'm going to multiply through by the least common multiple. Let's expand that. So when I multiply x minus 2 times 2 over to this guy, I get x minus 2 times 2 over x minus 2 is equal to 5 times x minus 2 times 2 over x minus 2 minus x minus 2 times 2 over 2. So be careful. This negative comes along for the ride. But now we can do some cancellation. I have cancellation here. I have cancellation here. And I have cancellation here. Now we've reduced this to a linear equation. This is 2 times x is equal to 5 times 2 minus the quantity x minus 2. This is 2x is equal to 10 minus x plus 2. I can add x over to get 3x is equal to 10 plus 2, which is 12. And we can divide by 3 to get x is equal to 4. So all rational equations, I'll say, degenerate to linear equations. That's been the trend for all of these. These rational equations where x is in the denominator, every time we've done some type of simplification, it's always turned into a linear equation. So you need to make sure you're okay with solving linear equations. Otherwise, you can't have any, it's going to be very difficult for you to solve rational equations because the point of solving a rational equation is to get it to a linear equation. So you want to be able to solve it when you get to that bench point. So that's it for today. I've ran out of time. We'll talk a little bit more about this on Monday, and we're going to do some harder examples. But if not, you're free to leave. Make sure the quiz is now available. It will be due Sunday. Maybe I'll push it to Monday. I need to look at the quiz again to make sure that you guys can do all the questions. If you guys can't do all the questions, I'll push it so you guys will have access to the knowledge to actually complete all of the questions. But I'll send an announcement about it. Other than that, have a great weekend.
Thank you.
Thank you.
Yeah.
And the worksheet you already The file is already up to submit it, correct?
Yep, it is.
Okay, thank you.